Dear users of this presentation, the topic is about the data and its analysis, conversing with data analysis with data thanks to the variety of colors. As is well known, analog data is measured against continuous quantities, for example, length of a ruler, heights of a mercury column in a tube, a logarithmic ruler for calculations, etc. While numerical data are mapped to discrete quantities, for example, ticks of a clock, beads of an abacus, open and closed electronic circuits, etc. Digital data, as well as digital math and graphics, dominate modern data analysis. Professor Nikolai Tomchev is the creator of this presentation. He is the author of a computational approach called DefMod, registered in the Bulgarian Patent Office. I'm a student, Johan Kirillov, and I'll be happy to make this presentation to you. Our DefMod approach entirely works with discrete data. All analysis and optimizations are done with them. For this reason, this presentation includes all the basic knowledge necessary to know when applying our approach. Indeterministic data refers to numbers with or without units of measurement and attached. They are too poorly understood to relate to the parameters of some research. However, their research using graphical, dimensional, and statistical methods can be converted into deterministic data that estimate the effective in the future, the parameters for modeling or forecasting. Data describes dependent and independent variables and applied units of measurement. In electronic computing, a data array or matrix of dependent variables in a regular sequence is a basic format for analysis because the independent variable information requires no storage. Rather, it can be calculated internally using the start of the array and the sampling interval. With the advent of electronic computing, the matrix has become the dominant mode of modern data analysis. A matrix is a rectangular array of numbers or elements indexed by their row and column numbers. A symmetric matrix has elements symmetrically distributed about the diagonal. Transposing a matrix involves swapping the rows with the columns. The rows and the columns of a matrix are often called its corresponding row and column vectors. Matrices with the same numbers of rows and columns can be added element by element. Multiplying a matrix with k columns of n rows by another matrix with k rows of m columns consists of n by m elements, where each element is the sum of the corresponding element row by column. The above several matrix concepts driven by electronic computing offer significant advantages in modern digital technology. The same units of data can be added, subtracted, multiplied, and divided. For the equation to be valid, the units on both sides of the equal sign must be the same. That is, the equation must be dimensionally homogeneous. Units of measurement are based on length, mass, time, temperature, and other primary or base dimensions. Data standardization makes it dimensionless and simplifies its processing. Deterministic data can be related to the parameters of a prior model by inversion, while non-deterministic data lack a model to quantify. Thus, to transform non-deterministic to deterministic data, efficient models are developed using analytical procedures such as calculus, dimensional analysis, and statistics. The figure presents a simple classification scheme for data in terms of their basic analytical properties. Specifically, the data ranges from non-deterministic to deterministic numbers with or without units of measurement attached. Non-deterministic data cannot be described by analytical or mathematical expressions involving natural process variables, and must therefore be investigated using numerical calculus, dimensional analysis, and stochastic methods, i.e. statistical analysis. In contrast, deterministic data are numbers with or without units of measurement attached that can be related to equations based on natural process variables. At their core, people act as collectors with a tendency to collect or sort and classify their observations in a given research. The resulting information is usually provided for use and reporting of observations. Figure 2 presents a simple classification scheme for data in terms of their basic analytical properties. The data Bij and AI are defined by two basic elements of information, which include the dependent and independent variable quantities, Bi and AI, respectively, together with their applicable units of measurement. In electronic analysis, the data involved as a collection or set of individual data points require maximal processing, such as a time and storage commitment to accommodate both of these essential elements. However, when the data is formatted as a uniform sample or grid array in one, two, or more dimensions, it is important that the data addresses and values or amplitudes by ij in their correct order or sequence. All computational efficiencies are also preserved in the mathematical processing of the data array or matrix. Matrix algebra was created in the early 20th century. Difficult implementation by manual calculations is compensated by working with a computer. In this regard, popular linear equation solving programs, for example MATLAB, Mathematica, MathCAD, or etc., are widely used, which allow users to make calculations easy to manipulate through analysis matrices. Accordingly, with the advent of electronic computing, the matrix has become the dominant mode of modern data analysis. Addresses and sample data sizes, these addresses for a 3x3 matrix are shown here. Common matrix relationships for forces, density, specific gravity, stresses, work, energy, moments, and various modules are expressed in terms of primary or base dimensions of M, mass, L, length, T for time. Dimensionless quantities are denoted by the number 1. Most of the discrete engineering problems are difficult to quantify. Usually, they are studied using large-scale modeling experiments. This applies both to the design of rational structures and to the determination of optimal technological processes. Effective scale modeling experiments require that the model and prototype maintain geometric likeness and similitude. Geometric similarity involves scaling all geometric dimensions so that their ratios are equal on the model and prototype. Kinematic similarity equalizes the relationships of time elements, velocities, and accelerations between them, the model and the prototype. Dynamic similarity, on the other hand, involves scaling all the forces so that their ratios are equal between the model and the prototype. Similarity is established when all three conditions for similarity described above are specified and met. However, in practice, it is often impossible to satisfy all similarity requirements simultaneously. What follows now are must-know summaries of data and data processing. Data are numbers with or without attached measurement units, which are classified as non-deterministic if they cannot be modeled with direct quantitative separation, and deterministic when they can be related to a modeling equation based on the research parameters. In general, research parameters can be related by numerical, statistical, and dimensional analysis to non-deterministic data and by inversion to the deterministic data. Data consists of dependent and independent variable quantities that may be associated with units of measurement. The dominant format for electronic analysis is a data array that expresses only the dependent quantities in a proper order or sequence of independent variables, necessarily computed internally from the array origin and sampling interval. A few basic concepts such as rules and definitions for arrays or matrices dominate electronic computing. A very small group of matrix operations dominate electronic computing. This group includes adding and subtracting two matrices with a total number of rows and columns, multiplying a k-column matrix by a k-row matrix, taking the inverse of a matrix where the number of rows or columns is equal, and this is possible only if the scalar value of its determinant is non-zero. Units of measurement are based on length, mass, time, temperature, and other primary or base dimensions. Data standardization makes it dimensionless to simplify its processing. Standardized data have zero mean and unit standard deviation. They are obtained by subtracting the mean of the data from each data and dividing the difference by the standard deviation of the data. All measurements and their subsequent calculations contain errors that must be evaluated in effective data analysis. Statistics is an essential tool for quantifying errors. Systematic errors are the result of repeated but incorrect results entered during the data collection process. They are difficult to evaluate statistically. Systematic errors result from faulty measurement equipment, observer bias, for example, read error, or etc., and other repeated but incorrect results. Random errors result from imprecise measurements that give random fluctuations about the true value. Statistics can determine whether fluctuations are random. Random errors result in random fluctuations of the observed values from the true values. Statistics can be used to determine whether the fluctuations are random, but these errors can also be summed in practice. Calculation errors are the result of data rounding, from truncation calculations or other computational transformations. Both statistical and non-statistical estimates are used to deal with these errors. Sampling errors due to improper sampling can be systematic or random, and thus can be addressed by non-statistical and statistical estimates, respectively. Accuracy refers to how closely a measurement approaches the true value of a known or assumed quantity. Accuracy refers to the repeatability of an observation, where absolute accuracy expresses the observation plus minus error in the same units as the observation itself, and together with relative precision gives the error as a fraction or percentage of the magnitude of the observation. The number of significant digits of an observation is the number of digits that account for the value without loss of precision. A number can be rounded by adding 1 to it, only if the digit to the right is greater than or equal to 5. The shaded area in the upper right-hand corner is the second-order region, ignored when evaluating the first-order error in the region by Taylor's theorem. The same can be multiplied from areas into volumes. In the next few slides, we will also introduce some key concepts from the field of statistics and regression analysis. First, modern data analysis produces results along with corresponding statistical error measurements based on the data mean and variance. For a small data sample with n small or equal to 15, variance is taken as the sum of the squared deviations divided by the degrees of freedom, v equals n minus 1. Instead of n, which is appropriate for larger data sets. 2, for the error of a function with measured parameters and parameter errors that can be estimated using Taylor's theorem, the resulting variance distribution rule, for example, reveals the variance function as the sum of the variance of each parameter multiplied by the square of the variance of the function with the corresponding parameter. The standard error of the mean, on the other hand, is the ratio of the standard deviation of the data to the square root of the number of data. Third, approximated by a histogram, the statistical distribution of data summarizes their integral and differential properties in terms of mean and variance. Statistical error bars and inferences for the data are obtained by assuming that the probability of finding the value of the dependent variable in an interval of the dependent variable is given by the area under the curve in the interval, where the total area of the distribution is the total probability, or 100%. Fourth, widely used distributions in research and engineering include the binomial distribution, which governs discrete processes involving a fixed number of independent trials, each with only two possible outcomes. It estimates the odds of getting different combinations of n things taken x at a time. The frequency distributions for the data are listed in the figure and include a frequency polygon, relative or differential frequency distribution, cumulative or integral frequency distribution. Fifth, perhaps the most widely used distribution of all is the mean-centered bell-shaped Gaussian or normal distribution, where approximately 68.3%, 95.5%, and 99.7% of the data are contained within plus minus 1, plus minus 2, respectively, and plus minus 2, 3 standard deviations from the mean. The Gaussian or normal probability density function centered on the mean data and divided into 8 probability intervals in integer multiples of the standard deviation. Thus, the chance of a distribution value falling within the range of the interval k equals 5 is about 34%. Given that the chance is roughly doubled to find the value in the range, which spans the intervals k equals 4 and 5, the chances rise to approximately 95% and above 99 for the value to fall within 2 and 3 standard deviations. Sixth, as a consequence of the central limits theorem, for data samples n is greater or equal to 25, the means follow a normal distribution with standard confidence limits based on the errors. These confidence bounds can also be compared to infer different origins of the data sets. Seventh, for poorly sampled data, roughly numbered n below 25 with an approximately normal or bell-shaped distribution, statistical error bars and inference testing were established using the weaker student's t-test. Confidence, and eighth, confidence intervals of the variance of normally distributed data were obtained using the distribution. These differences in data can also be tested to infer the origin of different datasets using Fisher's F distribution, with coefficients of variance for datasets drawn from a normal population. Ninth, analysis of variance, ANOVA, partitions the total variance between two or more datasets within the sample, among the sample and other significant components using the F distribution. The goodness of fit test uses a distribution to assign the data to a statistical distribution by comparing the observed and expected data for densities in 8 or more probability intervals of the expected distribution. 11th, somewhat weaker non-parametric or distribution-free statistics can be established by ranking or otherwise organizing the data within a sample into parameters that are independent of the shape or format of the probability distribution of the data. For example, inference about a mean-centered distribution of data can be tested by subtracting the mean from the data to determine whether the numbers are negative and positive, and the residuals are approximately equal. First, Least squares linear regression estimates the parameter of the input-output interaction law and the slope of a straight line with least squared deviations from the straight line data. Second, least squares intercept and slope estimates come from solving a system of linear equations obtained by differentiating a residual function involving the sum of the squared differences between the data and the linear model predictions. Equations minimize the residual of the function between the experimental and predicted values. Third, the desired measures of fit of regression performance include minimization of variances, slopes, and predictive deviations, and confidence intervals, as well as maximization of the correlation coefficient and ANOVA test of significance of the fit of the predictions to the data. Fourth, the intercept and slope variances are typically propagated by assuming either uniform or Gaussian distributions in the dependent variables of the data. Fifth, for uniformly distributed errors in the data, the parameter biases are based on the variance of the data, which is known or estimated from a previously known residual function, where the residual function is divided by n-2 degrees of freedom. Sixth, for normally distributed errors in the data at each observation, this is assumed to be from the Gaussian error distribution. Thus, maximum likelihood estimation of the intercept and slope parameters requires a modified residual function with each term partitioned by the variance of the error distribution of the corresponding data point. Seventh, statistical error bars or confidence intervals by the intercept and slope are estimated primarily from weight standard deviations of the parameters multiplied by the value of the t distribution at the desired alpha significance level. For n-2 degrees of freedom. Eighth, prediction confidence intervals refer to a comparable product with the desired t-value multiplied by the standard deviation of the predicted differences with the data. Ninth, the correlation coefficient is the square root of the coherency coefficient, which varies between 0 and 1. It gives the percentage of observations that fit the straight line model. The statistical significance of the correlation coefficient is directly related to the number of data and can be tested using the normal distribution. 11th, the statistical significance of linear regression can be tested by a ratio of the mean squared deviations of the predictions about the mean data to the mean squared deviations of the predictions around the data in the ANOVA table. As long as the ratio is less than a critical value of the F distribution at the desired significance level and degrees of freedom 1 and n-2, there is no reason on the F-test to reject the hypothesis that the data did not fit the estimated straight line. And 12, general classical linear regression minimizes the sums of the squares of the deviations in the dependent variables of the predictors and observations, assuming constant error in the observations. Thank you for your attention and time, and do not hesitate to ask questions on our mail, tonchif@vtu.bg, and at our website. And thank you for your attention and time.